Okay, so let's continue. So for the project as well, you have to, of course, work with variables, and we said that you have to have at least 2 continuous variables to help you do the response surface method, the optimization at the end. Yeah, so this is an issue for some of the groups anyway, to think of a response variable that you think may have some type of optimum. Okay, so if you have something which is kind of, if you keep increasing the time and keep increasing the variable, it keeps increasing. It's going to go, keeps going. It's going to be difficult to do the last part of the project. So try to find something in the response variable which is has some type of optimum. Okay, if you can do that. So if you're clever, you can transform your response variable into something which may have an optimum. Okay. So yes, so some people have asked me, yes, is time a discrete random variable? What do you think?
It depends on how you are controlling the time. Sometimes you can only control it by moving between intervals. So, for example, in a microwave, you can't control it. You have to, well, in the microwave I have, you can only go to 1 minute or 2 minutes or 3 minutes. You can't go in between.
Right. So what do you think? Is it a discrete random variable? Sometimes. On your microwave it is?
Yeah, it depends on the equipment, but if you have a timer, a clock, it's a continuous, well, like this in a cell phone, it's a continuous variable.
Right.
So it depends on how you are controlling it.
Okay. So, yeah. I would say it's a continuous random variable time, because you can at least imagine that you can determine the time in a continuous fashion. Maybe your equipment doesn't allow you to, but at least conceptually you can go. The example given here of something which is discrete is the number of defects. On a semiconductor, you cannot have half a defect. It's a defect or it's not a defect. So that's a discrete random variable. Okay. So you may have other examples then. Number of persons in a group. You can't have half a person. So it goes by units of 1. Okay, so that's, I would say, things like time, space, length, weight, they're continuous. If you have something like number of persons, defects, let your imagination work. Mine isn't working at this moment. That's discrete, okay? So that's hopefully clear then how that works. If we do discrete random variables, we don't have a PDF, a probability distribution function, but we have a probability mass function. So we indicate the probability of having this particular value. And that's also then at that point only defined, so it's not really a function. As we've seen it in the distribution function for continuous variables, but here it's like also a discrete function, a function only defined at the values which are possible. So we call this a probability mass function, or PMF, as opposed to probability distribution function, or PDF, as we did last time for the continuous random variables. And so we have this function which is then defined at discrete points, and it gives us the probability of having that particular situation or that particular value. We can also make this into a cumulative distribution function, obviously. And instead of taking the integral of the function, we sum the values. Okay, so the probability of having the discrete random variable smaller than a certain value is then the sum of the probability values for all the discrete random variables which have a value smaller than this small x. Okay, so that's a cumulative distribution function. This is an example of such a cumulative distribution function. So of course it's a stepwise function. As you increase with the probability of having this value of 1, you increase there with the probability of having value 1, and so on and so forth. So I think that's all clear.